name is Serra. So today we are continuing yet with another series on statistical testing using R. And in this video we are gonna be talking about normality testing and t-tests. So before going into statistical tests, it's important to understand what they mean. For example, let's think of a clinical trial. So for having a new medicine go on to the public, we have to do clinical trials where we have some control groups that take the placebo and the group that takes the new medicine. But how do the healthcare professionals actually decide if this new medicine is effective, if it makes a difference? So here is where the statistical testing comes into play. The statistical test compares the two data groups which got the placebo and the new medicine basically, and then looks at the ranking if it's a non-parametric test we are using, or the mean, median, these kind of things to compare the two groups and decide if the difference is statistically significant. And we will all learn about these. But before that, let me clarify parametric and non-parametric tests. So parametric tests are the tests we can use when our data is normally distributed. So when it conforms to the assumptions of normality. And then non-parametric tests are the tests we use when our data isn't normally distributed. And to understand that, I didn't want to immediately go to different statistical tests and teach you that. And before that, I want to talk about how you can understand if your data is normally distributed. And there are some ways which we will look at, like creating an histogram, which will help you understand if your data is normally distributed by just looking at it. But if you want to be sure, I will give you some statistical tests that will test the normality of your data. So let's start. Here I create the R markdown file, and first of all let's start with the histogram. Let me create my data. We will use R norm here. So the n here, the parameter, as you can see above, gives the number of samples, which I will give as 100. I want 100 samples, can choose anything else you want. And then we specify the mean and we give the standard deviation. So the R norm function basically chooses random numbers, random 100 numbers from a normally distributed data with a mean of 15 and a standard deviation of 2. Now let's create our histogram. We use the hist function for that, and if you wanna look at it, when we create it, we can actually see how the hist works according to the parameters. You can always go to help and look at it too. I will give the data first, and then we have 10 breaks, and then we have the color, which we can give anything. Let's give red. Then we give our title. Let's say histogram of data. And then we can also give titles to the x and y axis. And let me give a title to the x axis now as values. Can also give a title to the y axis with ylab. And now let's plot this. And here we can see our data. To be honest, it looks like it's slightly right skewed. Right skewed means it has a tail on the right, as we can see, but it's almost normal. You can try it again. It chooses random numbers and you can get a better normal distribution from that. This looks a little bit better. Let's try some more. I think this looks, yeah, almost normal. I will use this data for normality test, so I don't want to use a data that is normal distributed for that. So let me insert another R block, and let's continue. So another factor here that you can look at are the z-scores. So z-scores measure how many standard deviations a data point is away from the mean. So by plotting the z-scores of our data, we can see if most values cluster around 0, which represents the mean in a z-score plot. And then what we would expect is most data values should fall between -3 and +3, and you can look at the percentages for that too. Normally approximately 68% fall between -1 and +1, and -2 and +2 have approximately 95%, and -3 and +3 have approximately 97% of the data normally. So let's see. Calculating the z-scores is really easy, especially if you've taken statistics. I'm sure you've seen those. And then from our data, we get the mean of our data and subtract. So here what it does is, for each value it will take that value and it will subtract the mean from that value, and then it will divide that result to the standard deviation of the value. We give the whole data, but it goes like this. And then now that we've calculated, let's go and actually plot it again with a histogram. We have the z-scores, and then breaks 10 for color. Let's give yellow. My background is yellow today. And then let's give the title again. This time it's not the histogram of data, it's the histogram of z-scores. And then we can also give the x-axis label. I was saying title all the time, x-axis title. What I meant was label. It comes from xlab, x-label. Can remember it like that. And let's say z-score. Okay, this would work. And as you can see, most of our data is clustered around 0, and they like mostly fall between -3 and 3, -2 and 2 also. So this also shows that our data is normally distributed. Another plot that we can look at is the QQ plot, which is the quantile plot. So what a QQ plot does is it compares the quantiles of the sample data with those of a normal distribution. So if the data is normally distributed, points on the QQ plot should align closely with the red line, and you will see it when we plot it. Now let's plot it actually. That's all it does. For this we use QQ norm and put our data in it. We also want to see the line, right? If it aligns with that line. Put data, and because we said red line, let's give it the color red. And as you can see, they are so close to the red line. So as we have also talked about here, this is really normally distributed because it's so close to the red line. And although there are some slight deviations at the ends, we would expect that most data are around 0, and that's good. So also one last thing, these slight deviations are due to the sampling variability, because if you sample from a population, you won't be able to exactly match the mean or the standard deviation or so of that population. There will be a variability around the samples, but you want it to be almost almost 99% or above 90% representative of the population. And as I've given in my article too, let me give you a little statistical info. So as we talked about in this plot, quantiles split a data set into intervals, helping us to understand the distribution and spread of values. So here, commonly used quantiles are quartiles that split the data into 4 equal parts, and then we have the deciles that divide data into 10 equal parts, and we have the percentiles that divide data into 100 equal parts. And if you've taken statistics, quartiles and percentiles are used a lot. We have, for quartiles, we can see them best in a box plot, because in a box plot you have the first quartile after the whiskers. That's like the first part of the box we have in the middle, and the first quartile represents the 25th percentile, so which means that 1/4 of values are below this point. And then we have the median in the middle, which represents the 50th percentile, so 50% of the values are below this point. And then we have the third quartile, which represents the 75th percentile, so 3/4 of values are below this point. And then we have 100% of the values if we go to the end of the box plot with some outliers too. So the box plot gives everything about it. I wish I could show it here, but you can always go to my article and see the box plot I put there. And the difference between Q3 and Q1, which are the third and first quartiles, is also called the interquartile range. And another thing we will always hear about during this series is the null hypothesis and the alternative hypothesis. So the null hypothesis is the idea that there is no real effect or difference between the groups or conditions we are studying. So it assumes that any observed differences in our data are due to chance. So for example, if we are testing whether a new drug is effective, it will say that the drug has no effect compared to a placebo. And the alternative hypothesis is the opposite of the null hypothesis. It suggests that there is a real effect and this medicine really makes a change. We don't know if it's good, if it's a good change or a bad change, but we will further look at it if we actually prove that the alternative hypothesis is true. So also an important thing is the p-value. If you remember, I mentioned that we look at if the difference is statistically significant in the beginning of this video. So basically p-value tells us that. It helps us decide if we should reject the null hypothesis, because it represents the probability of getting results at least as extreme as the ones you observed, assuming the null hypothesis is true. So basically what I mean by here is, can we have gotten this value if by random chance? A low p-value, usually the threshold is 0.05, means that the observed data is unlikely if the null hypothesis is true. So we can reject the null hypothesis and say that this difference is statistically significant. And the high p-value above 0.05 tells us that we should accept the null hypothesis basically and say that we don't have enough evidence to say there is a difference between the two groups. And now let's move on to the statistical test for normality. Firstly, we need to know that if the data follows the normal distribution, we expect high test statistics and non-significant p-values, typically above 0.05. If it's below 0.05, it will say that our data doesn't follow a normal distribution. So let's start with Shapiro-Wilk test. I thought of maybe I can create a like a small title here. Okay, so Shapiro-Wilk test checks how close our data is to a perfect normal distribution by assessing each value's fit within a normal distribution curve. And as I mentioned before, a high W value, we will have W values as a result closer to 1, and the p-value above 0.05 suggests that the data is approximately normal. Now let's test it with our data. So for this, it's so simple. We just say Shapiro.test and it gives us basically, and then we give the data inside it. And as you see, it's really close to 1, the W, and the p-value is very much above 0.05. Our data is normally distributed. Now we have another test. I want to give you as much tests as possible so that you can decide on which one to use, because they have some slight differences between each other. So then we have the Kolmogorov-Smirnov test. Oops. So this test compares the overall shape of our dataset distribution to a normal distribution. Here it calculates a capital D value based on the biggest difference between the cumulative distribution of our sample and that of a normal distribution. So here we need to know that a low D value and a high P value indicate the sample distribution doesn't differ significantly from a normal distribution. So it means it's normally distributed. For this, we just say ks.test, we give our data, we say p norm, and then as mean, we give the mean of our data. And then as standard deviation, we give the standard deviation of our data. And the p-norm here is the cumulative distribution function, and it gives us the probability if like the normal distribution we are testing against is similar to the distribution of our data, because we had a normal distribution with a mean of 15 and a standard deviation of 2, but we chose 100 random samples. So with that sampling variability, it might not have been as normally distributed as we wanted. So that's why I ran it over and over again to get a better normal distributed data. Now let's run this. Okay. So as we can see, D is very close to 0, and in the beginning I said that a low D value and a high P value indicates that the data is normally distributed, and the P value is really above 0.05. So we again say that the data is normally distributed. Okay. Now let's move on to our third test, which is Anderson-Darling test. Anderson-Darling test. So I'm also looking at my article if I'm forgetting to say something that I've written, but you can both look at this video and the article on the site too, because we move synchronously with the article. Okay, so in a Anderson-Darling test, it is similar to KS test, Kolmogorov-Smirnov test, but it emphasizes the tails of the distribution, making it more sensitive to deviations in the tails. So if your data has some tails, like it's, as we said in the first one, we got that it was slightly right skewed, this test will really look at that and emphasize that, and it might reject normal distribution, whereas the two before test might accept it. So we can come up with these kind of situations. We need to know which one to use. For this, you can say, if you don't have this package, install that package's nor test. But since I have it, I will just comment this and then just call that package. And it's really simple. Again, we say ad.test and we give our data. So in this case, the high p-value supports normality, and if tails differ from normality, this test will capture those deviations more clearly, as I mentioned. So here we have the a value as 0.17 and p value is much larger than 0.05, which says it's like normally distributed. But in this case, the a statistic says that the a value here also uses the CDF, basically the cumulative distribution function, and because it's really less, like close to 0, it means that it doesn't deviate much, which is good. But I still, as I did in my article, I want to show you how it's different from the other two tests. For that, I've chosen another data. Can also just change it here. Let's give a standard deviation of 3 here. See. This looks like really left skewed, so I think it's better to use this. If we look at it, it's not really, oh, my bad. As you can see there now, not most of the values are clustered around 0. I think this will make a difference. Let's apply the tests again. First, let's see this. And you can see that the tails really start deviating here. And the values, there are more values on the tails this time. And then let's apply all 3 tests. Okay. Now you see that it gives, like a compared, when we compare it with 0.17, 0.95 really changed it, because it says that there are deviations on the tails. Tails deviate from normal distribution a lot. And here we can see they didn't change much. W is still close to 1 and D is still close to 0. So these aren't really looking at the tails that much, and they don't make as much difference as the Anderson-Darling test did. So let me summarize these 3 tests again. The Shapiro-Wilk test checks whether your sample data follows a normal distribution by comparing how close it is to a perfect normal distribution, and it does this by looking at each data point and comparing it to where a perfect normal point would be. And then we have the Kolmogorov-Smirnov test, also known as KS test. which compares the overall shape of our sample's distribution with a perfectly normal one by looking at the cumulative distribution. The cumulative distribution shows the percentage of data points that fall below a given value. And then we have the Anderson-Darling test, which is similar to the KS test but gives extra weight to values at the extreme ends, so the tails of the data. This means it's more sensitive to whether our data's tails match those of a normal distribution. And I've given a table in my article which you can look at it too. And finally, we are moving on to parametric tests. So let's define it again. Parametric tests assume that the data follows a normal distribution and are typically used when comparing means or examining relationships with a normal distributed data. So in all these tests, we have some assumptions, which are conditions that must be met before a test can be conducted, and we will check for all of these for each of our tests. So let's start with the t-test family. We have the one sample t-test first. So the one sample t-test is used to determine if the average of a single group of data points is significantly different from a specified value. And we will give that specified value when we are talking about this. Let me put it here. Okay. So this specified value is generally called the population mean, and this test is useful when you have a single set of data and you want to see if it differs from a known average. So, for example, you have the test scores of a single group of students. You are their history teacher and you want to see if the score is better than last year's score, for example, or you go into US average history test scores and you want to compare it with that, whatever you want. And then when you look at when you calculate the average of those scores, if their average scores differs from the general average you got from the website, for example, it means that basically it differs from that known value. And that was the t-test. So now let's look at the assumptions. First of all, data is normally distributed, as we've talking about it, and then the sample is randomly selected and independent. It's really important to randomly select samples from populations, because then we can say prove the null hypothesis, and we can say the sampling wasn't biased. Independent means each data point in the group doesn't influence any other data point. If we have a dependent test, which we will see in the dependent t-test, it means that you measure something, some value of an individual, and you measure after some time again. So it's the values of the same individual, so they are dependent in this case. But since we have a single group, all the individuals are different and they are independent. Okay, now let's do this. We can first set a seed before creating our data, so we have the same data, because it changes every time, which is kind of annoying. And then we have the rnorm function. We can have 30 data points, mean of 18, standard deviation of 3, and then let's apply the t-test. Sample data. And now this is the important part. Mu is the known general average that we've talked about, like the population mean, for example. And in this case, let's give it as 20. Now let's do this t-test. Okay, we've gotten the results. Now it's time to interpret them. So first of all, we have the t-value as minus 3.9851. This indicates the size and direction of the difference between our sample mean and the hypothesized population mean of 20 we've entered. So a negative value means that sample mean is lower than 20, which it is, it's 18. The larger the absolute value of the, we didn't calculate it, but it must be approximately 16 point something in this case, because these are 30 random samples, and we sum up their values and then according to that get the average. So sample mean is lower than 20, we know that. And if the larger the absolute value of the t-score, the greater the difference from the hypothesized mean, which is expected. If we've gotten minus 5, it would be 5 lower than the mu we entered. So the degrees of freedom is a term we will hear about during this series, and it represents the number of values in a dataset that can vary when estimating a parameter like the mean. So for a one sample t-test, df is calculated as the sample size minus 1. We always give it as minus 1 if we have one group, but it changes when we have more than one group, and we will see about in the future. And then this adjustment accounts for the fact that one value is fixed by the sample mean, making the rest independent. So that's why we subtract 1. And here with a sample size of 30, we get 29 degrees of freedom, which is 30 minus 1, which influences the shape of the t-distribution used to interpret the test results. Okay, we have our p-value, which is very low, is 0.000 something, and it suggests that the observed difference between the sample mean and 20 is statistically significant. And we can strongly reject the null hypothesis, which it gave here, which we can derive from here, because we have the alternative hypothesis which says the true mean is not equal to 20. Then the null hypothesis will say the true mean is equal to 20, which it's not in this case. Then we have 95% confidence interval, which we will see throughout this series again, and it's between 16.76 to 18.96 approximately. This range, this basically provides a range in which we can be 95% confident that the true mean of the population lies. And since this range does not include 20, it further supports that our sample mean is significantly different from the hypothesized mean. So this is very useful in the interpretation. And we basically reject the null hypothesis because of this confidence interval result and the p-value. And now let's move on to independent, also called the two-sample t-test. And you might be saying, oh, we have two groups here, and you are right. It was one sample t-test and we had one group. Okay, so the independent t-test, also called the two-sample t-test, compares the averages of two separate groups to see if they differ significantly. And this test is commonly used when you have two distinct groups, such as a treatment group and a control group, and you want to compare their means. So an example scenario again might be that you are a researcher and you want to compare test scores between two classes, one that received additional tutoring and one that did not, which is a good statistical test you can do as a researcher in education. And then what are our assumptions? As always, both groups need to be normally distributed. And then here comes kind of a thing that will go more in depth, and here it comes. The spread or variability of the data in each group should be about the same. What does this mean? This is called the equal variances, also called homogeneity of variance, meaning that the data spread or variability should be similar in each group. This basically means that the range of values in one group shouldn't be significantly wider or narrower than in the other group. If the variances are very different, it can affect the accuracy of the t-test results. So for that, we will learn about some tests that you can use to test for the variance. And we have for that the Levene's test and the F-test. So let me give you the Levene's test first. It's kind of strange that I'm giving more and more tests before my second statistical test. But it's good to have a lot of tools that you know. So the Levene's test checks if two or more groups have similar variances by focusing on the absolute deviations of data points from the group mean or median. So it basically calculates the absolute difference between each data point and its group mean, and then compares these deviations across groups to see if they differ significantly. So let's see our code. And one last thing, it's generally preferred when data might not be perfectly normal because it's robust to slight deviations from normality. If it deviates a lot, this might give really strange results. That's why we are using Levene's test for parametric test, and we will see other tests for variance testing in non-parametric tests. So the interpretation is quite easy to remember. We just look at the p-value again. If it's less than 0.05, it's statistically significant, which means that it suggests variances differ significantly. Okay. So we want to basically get a p-value above 0.05 to say there is no significant difference in variances. And the code we will use here is Levene test. And then we have group 1 and group 2. Good thing I could find, I could find this symbol. It's quite hard to find in the keyboard. We have vector. I will talk about this once I write it. Each and then group 1's length. Okay, so it basically compares the group 1 and group 2 with the fact, like we are basically creating a data set in here in this part that gives 1 and 2. So basically the Levin's test has to have the two groups as a single vector. Here is what we do. As you know, the C creates a vector out of the elements we give it to, and then we have the rep function which basically repeats 1 and 2 after each other for the length of group 1. Which does, like, it does this because we need to indicate which value belongs to group 1 and which value belongs to group 2, because we are combining them as a single vector, and how will the Levin's test know if this value belongs to group 1 or group 2? And then we basically turn it into a factor, and that's this code. Oh, I could never have thought of this as such a hard thing to explain. Let's see my article, if I wrote it wrongly. I might have. Levin test. So to use the Levin test, you have to install the package car. I thought I had it, but apparently I didn't. So you can install it like that and then just call it. So before using this, let's create group 1 and group 2. It's really easy in this case because we just create random distributed data. We have 30 samples. Mean, let's take 18, standard deviation 3. I wanna see the difference, so let's give a different mean this time. 30 samples again, mean 21, standard deviation 3. We want, I will use this data for testing the independent t-test. That's why I've given different means. But for the standard deviations, let's see if they deviate a lot, because I've given 3 for both of them, but they might since they are random. We will see. Now let me run this again, and hopefully yes, it worked great. So when we look at this, we again see the degrees of freedom, and we see a new thing, the f value, and then this is basically the p value. So the degrees of freedom says that we have two groups, which we have, it's 2 minus 1, which is 1. As you know, we just take the number of samples or the number of groups and then subtract 1 to calculate degrees of freedom. And on the second value, 58, now it changes a little bit because it refers to total degrees of freedom for the error, which typically is the total number of observations minus the number of groups. Here we don't subtract 1 anymore, we subtract 2 because we have 2 groups. Since we have 60 samples, it's minus 2 is 58. And then we have the f value, which is 0.0132. This is the ratio of the variances. So basically the standard deviation without the square root means the variance. And then the variances of the groups being compared, if this value is close to 1, it indicates that the variances are similar, while a value much greater than 1 or much less than 1 indicates the variances differ. This is expected because if you divide two numbers, if it's exactly 1, it means the two numbers that you divide are the same. And if this value is close to 0, it means that the denominator is bigger than the numerator. And if it's bigger than 1, it means that the numerator is, so the variance of the group 1 is bigger than group 2. So this was very simple, and I like f value for that. Simple to understand. And then we have the p-value, which is 0.9088. So this indicates that the probability of observing the data if the null hypothesis, which says that the variances are equal, is true. So the variances are basically equal, and we couldn't reject the null hypothesis here. So this was kind of expected because we have given the standard deviations as 3 in this case. So they have the same variance if the variance is just the like standard deviation without the square root. But if we change the standard deviation, what would happen? Shall we see? Oh no, not 45, that would be... Ooh. As you can see now, it's less than 0.05, and it has even given a significance code to that. So as you see, by changing the standard deviation, the variance changes, and now we can't, we reject the null hypothesis and we say that the variances are different, which would mean we can't use the independent t-test because we couldn't conform to one of the assumptions. Since we wouldn't want to do that, let's just keep it as 3 and move on to our second test, which is the f-test. F-test. So the the f-test also compares variances, but is only applicable for 2 groups and works best when the data are normally distributed. It calculates the ratio of the variances between 2 groups. If this ratio is close to 1, the variances are likely similar, and if this ratio is far from 1, the variances are likely different, which we already talked about. But don't forget that that's applicable for only 2 groups, because in this t-test we have 2 groups, but when we go over to ANOVA we will have more than 2 groups and we can't use f-test, but we still have the Levene's test, which is good. So let's test it. This is fairly simple. What we do is we say var.test group 1, group 2, and then get our result, and we got it. So the f value here is 0.74356, and then since the f value is close to 1, it indicates that the variances are similar, while a value significantly less than 1 suggests that the variance of group 1 is less than that of group 2, which we've talked about. Sorry for repeating things again, but I want to make sure they're understandable. And then we have the num-df, which is degrees of freedom, and we have 29 in this case, which is, as you know, 1 less than the number of samples in group 1, because we also have the denom-df, which is 1 less than the number of samples in group 2. This means that in the numerator we have the group 1 and in the denominator we have the group 2. And then the p-value is 0.4298. So here we have the alternative hypothesis saying true ratio of variance is not equal to 1. So since the p-value is very much more than 0.05, we can't reject the null hypothesis, and we need to accept it, saying that the variances of the 2 groups are similar. And we have the 95% confidence interval, and this will make a huge difference, so be careful here. The confidence interval for the ratio of variance is given as between 0.35 and 1.56. This interval provides a range of values that likely contains the true ratio of variances. If this interval includes 1, which it does in this case, it suggests no significant difference in variances. So this 95% is one of the best tools you can use to interpret. And then we don't have anything else in this case, so we can move on with independent t-test. Finally, we use also t.test here. We give the group 1, we give the group 2, and then we say var.equal is true, so our variances are true, don't worry, and we get our result. So in this case we have again the t-value, which is minus 2.9292. This t-value measures the difference between the means of group 1 and group 2 relative to the variation in the data. So a negative t-value indicates that the mean of group 1 is lower than the mean of group 2. Okay, it was good to understand this. If it was positive, then the group 1's mean would be more than group 2's. Then we have the degrees of freedom, which is the total number of samples, which is 60 minus the 2 groups, 58. And then we have the p-value, which is much less than 0.05. So we can accept this alternative hypothesis that says true difference in means is not equal to 0. It's not, and we have proven it with this t-test. And let's still look at the 95% confidence interval. So we have minus 3 and minus 0. I will ask you that does this include 0? It doesn't, right? So this means that we really can reject the null hypothesis, and since this interval contains only negative numbers, it indicates that group 1 has a significantly lower mean compared to group 2, which is true, right? We had 18 as a mean here. Oh, that's the wrong one. And 21 as a mean here. in our distributions that we chose 30 random samples from. And that was all. Now we have the paired dependent t-test, which I've mentioned a little bit. We will talk more. Dependent t-test. So the paired t-test compares the averages of two related groups. Related here means that each data point in the first group has a corresponding data point in the second group, like a before and after measurement on the same individuals. And our scenario will represent that too, because now we are measuring students' test scores before and after tutoring. The same student has two test scores, so they are dependent. Okay, so the assumption we have here is that the data points are dependent and the data is the differences between paired observations are normally distributed. Okay, time to test. Before R norm, say 30, mean 20, standard deviation 3, after. Look, we have a linear dependency here that we put R norm 30 samples, mean is equal to 1, standard deviation is equal to 1. We wouldn't want it to the values to change 20 points or so. That would be really effective though, like the tutoring. Okay, and it's the same as the independent t-test, but now we have before and after groups, and we say that it's a paired t-test, so we say paired is equal to true. Okay, now we get our result. Let's interpret this again. The t-value in this case is minus 6.2664. So this measures again how far the average difference between the paired samples, in this case before and after R, is from 0. Since this t-value is negative, it indicates that the treatment is lower, the average value of the treatment is lower than the average value before, which is true because we just added for after the before values and then some more values. And the degrees of freedom is 29, which is calculated as n-1 as we've talked about it, and since we have 30 pairs, it's 29. And then we have the p-value, which is 7 point something, but it's with e minus 0.7, so it's really like less than 0.05, which means that true mean difference is not equal to 0. We accept this alternative hypothesis, we reject the null hypothesis. So we can say that the tutoring wasn't helpful in this case because the test scores after tutoring were less than before tutoring, which is funny in this case, but we could have thought of a better situation, which you will, I'm sure, in the future with your own data sets. And I think that was all from today, so thank you so much for listening. I want to cut the video here because we will be talking about the ANOVA test in the next video, and it involves more than 2 groups, so it's like t-test, but it's better when we have more than 2 groups. So because of that, I'm stopping here, and I don't want to make the video longer too. Have a great day and see you in the next video. Bye!